Thank you. My name is Aaron Costin, and today I'm going to be discussing about the requirement for ontology development in the AECO industry. My research deals with interoperability of all information, and this topic is more for our development, our area. So just as a show of hands, how many have heard the keyword ontology? Now, it's been thrown a lot recently. Okay. Of those who've heard it, who actually understands what an ontology does, or at least knows why we use ontologies? Okay, a few less. Okay, good. And so, for the brevity of the talk, I'm going to try to explain it as quickly as I can, but I do have extra slides after the fact to explain it more in depth. And so, if time persists, I will be able to explain that. So let's start back in fundamentals. So what are we? So our industry is information heavy. Think about it. You know, how much data tools software exists, how much information is out there, and everything that drives our industry, drives information modeling, is based on what? Data and information. And then the question begs is, how effectively do we use this information? Incorporated with this is the increased demands for speed and flexibility and convenience. We want all of it, and we want it now. And especially within a click of a button. And with the new technologies, we can virtually say that we want it. Hey Siri, okay Google, think about it. You know, the average worker, like us, you know, we have our bags, our tote bags that's given out in one hand. On the other hand, we have our lattes and coffee. On the other hand, we're tweeting about it. And so everything's about information, wanting it now. And so our landscape with our models has been shaped into a model-based information. Let's package all this information that we want in model form, send it off, and get that back, you know, instantly. And so achieving interoperability, which was discussed in the previous slide, has been a major challenge. And so it's all about how to get this information, sharing it effectively and seamlessly. So for my research statement, it is imperative that the information contained in the models can be shared and exchanged seamlessly and effortlessly by the end user. That's all what interoperability is. And so the purpose of my research is to develop a methodology that would enable the interoperability of multidisciplinary information models. And that's not just for our industry, but think about all the other industries that might have valuable information that we can use. And so it's not limited to one particular domain, although my current scope is for bridges. It has to be open and flexible, so any domain models. So think about our new advantages with smart cities, the Internet of Things, all this big data. We have all this information we want right now. And so the approach that's been recently utilized has been ontologies to capture, organize, and share information. So an ontology, is a formal abstract representation of the domain. It talks about the objects, concepts, relations between them. You know, it goes back to the train of thought of what is everything, why does it exist, and who are we are, and how do we describe this information. And so if you Google ontologies, make sure you include computer science in front of it, or else you go back to philosophy, which ontologies extend from. And so formally, it's written up in logic structure, first order logic, same logic that's in math, linguistics, philosophy. And the purpose of it is it provides semantics and a syntactic information to give everything meaning. And so there are machine-readable languages to help program this and implement it into software. Main uses include to share common knowledge, understand the structure of information, and most importantly, enable the reuse. So once you define something in ontology, we can reuse it over and over again. And most importantly, it's been shown to enable interoperability across our heterogeneous landscape of these models and systems. And so recently, in the last few years, there have been a plethora of ontologies. Some have been formally defined, some are just use cases simply. So they do exist in our industry. And so ontologies for the AEC have the potential to find the seamless information exchanged across domain. However, to do so effectively, it needs to follow various rules and requirements in order to do so. And today's topics I'm going to be discussing include the semantic logic, which are needed to be capturing information exchanges, understanding that there's actually different categories and abstractness to ontologies, understanding the different programming languages that we can encode ontologies. Finally, I will go over a few requirements and open up a few questions to have more consensus and industry alignment. So let's play a little game. So I'm going to flash a few pictures up here, and they have a single word in common. And I want you to come up with that word. One word describes all of these. Any guess? Bridge. Now, if I were to say, please give me the definition of bridge. Depending on what your background in, you have different definitions. So you have the same word with different meaning. Let's try this again. Did I hear beam? Beam? Someone say beam in there? Well, not really. We have joist, lintel, girder. And if you include more, you have purlin, spar, girder, bulk, timber, plank, support, strut. And so we have the same meaning, same functionality, with a different word. One more time. Somebody say it. Podium, right? Wrong. This, my friends, is called a lectern. A podium is a raised platform. That's what you step up. It's like a pedestal. And so their terms are used improperly, but semantics and the meaning behind that is understood. And so that leads us into the discussion of semantics. Semantics provides the meaning of an object, word, or phrase. It denotes what it stands for, establishes the rules for interpretation, and provides constraints for other interpretation of what it is. So example, in software. So just say we're modeling something. We want to model a table, but we use a door, right? We flip it over. We put plates and stuff on it. Is it a door? When you export it, will it have the door properties or will it have the table properties? Or you can have different objects, the same purpose. Now, how many objects can you use as a chair? Does that mean it's a chair as soon as you sit down? And finally, the erroneous naming. How many times have people have typos in their code that the computer can't understand? Or for the last example, lectern. I say, please step up the podium. There's no podium to step up here, but you understood what I'm saying. So with all that context is semantics. And so the goal is to have semantic consistency. So our human-based knowledge can be interpreted by the machine, and then the machine can send out those interpretations for others to read what we want. So the whole goal about this is to have consistency. So logic is the reasoning behind the development of ontology or how the domain works. So it's formally represented by description logic, and it includes axioms, which are stated rules or principles to help govern ontology. So these are assertions that the user inputs on their information to have those rules or requirements. For example, let's define what a subclass is. So that states, for all A and B, A is a subclass of B, given that A is a subset of B, and B is not a subset of A. Right? So that's the formal logic. We can use this example as a bridge. So suspension, girder, and arches are all subclasses of a bridge. And now then we can insert it into a language, and then we can have the description class and out. So these axioms are user defined about our knowledge. And so issues with some common programming issues. So when you think about it, data are just bits and bytes, ones and zeros. They have no meaning in context, right? And so the computers will do whatever the programmers are used to tell them, garbage in, garbage out. And so it comes down to the human issue. And one of these issues that as we could see now with IFC is if there's something that's not in there that cannot represent what we want, what do we do? We create it, we rewrite it, we extend it. There's no IFC. If there's a beam, joist, girder, if it's not this and that, let's define everything and constrain it to meet our desired needs. However, defining each object will bog down the schema, increase file sizes, you create redundancy. So if there's multiple ways of going about representing it, we might have some issues down the road. And so we need to minimally encode information to relay intent. And those who have knowledge about businesses, you might have heard the term MVP, minimal viable product, right? So how can we minimally code to get our intent out to what we want? And so that can be achieved by using semantics and logics via ontologies. So there are a few languages out there in code, but the most prominent one is called the Web Ontology Language, or OWL for short. Don't ask me why they call it OWL. I'm assuming because wool doesn't sound appropriate, or you can't have a little owl figure. And so, it's one of the many. It's used for semantic webs, meaning you can share information. They have a URI you can link into to connect it to. It has multiple export syntaxes, which are all interruptible. Although it's non-executable language, so you can view this more kind of like a database, although it's different than a database, and if there's time permitting, I'll explain the differences. There are various editors for ease in coding and implementation. This is a good thing. So people who don't really have a background knowledge of why we're doing ontologies can just download this and build their own ontologies. That's a good thing, but on the flip side, that's a bad thing, and I'll get to that later. And finally, there's been implementation of converting IFC into the web ontology language, which is called IFC out. And so there's recently publications on how to do this. So first start with the categories. There's three main categories. The first is called super ontologies. You can view this as the ontology of ontologies. This describes everything that ontologies mean. So merology, relations, part whole, parent, subclass. So it explains what something is. That extends into connections. So we define what something is. So how does it connect to something else? And finally, systems theories. So we have this object that's connected, part whole. So how does that relate to its surroundings? What other objects? What are the interactions between other objects? And these are specialized into what are called based ontologies. Now we get more into, defining ontologies for a domain, such as engineering. You're going to have the engineering process, you're going to have engineering components, and you're going to have the map that go behind. And at the bottom level is the domain ontologies. So these are the application basis. So when you see an ontology for actors, an ontology for structure, you're really looking at the domain because of the actual use cases of these homologies. And with the purpose of domain ontologies, you can be reshared. So let's take what you find over here, let's extend it over here and reuse it. And so together, these are the categories that all ontologies have to represent in order to relay their meaning and intent. So I'll give an example. So I'm doing work with bridge, and I want to design a steel bridge erection ontology. And so what do I need to capture? The math, equations, the people who are involved, material, bridge components, etc. It's possible and doable, and I can define anything I want. But the question asks, how long will this take? How long will it take one person to define everything involved in this? And the question is it feasible? Why define what already exists? And so look to see what's available. So I know there's ontology out there for engineering. You can use those, so I don't have to redefine it. And there's also others in our area, and etc. And so there is no one ontology. An ontology is actually multiple ontologies inserted. So it's often overlapped and shared. But important questions arise. Same thing with going into encoding this. How do we guarantee accuracy and integrity of what's been encoded? And how do we deal with obsolescence or change management? And these are just two of the main ones that pop up. And so the reason, and the way to get around this, is we need standardization rules and requirements in order to define these in a way that can be reused and shared. And so research has shown it needs to be clear and concise terminology, because go back to systems can then determine our intent. And I proposed using an industry-driven process. Going back to ontology development, you use what are called competency questions. What does this ontology need? Instead of saying, what does this ontology need, an industry approach is, what does industry need to represent with this ontology? Going back to that minimally viable encoding. Next, let's be sufficient consistency. It needs to meet the needs of the domain requirement and exchange information. I'm going to presented about the needs for COBE. So we've got to meet those needs. It can't have inconsistency, duplication, or over-constraining of definitions in ontology. It has to be reusable and extensible. It needs to be developed in a way to promote reuse and extensibility. If Joe over here does something with construction, he's going to have different actors, like a project management. If I have, erection over here, I'm going to need project management. So we actually are inscribing the same person, same actors. So there has to be a way that we can do it in a way so we can share that information. And finally, reliability and security. The beauty about ontologies is it's open. Anybody can develop it, and anybody can use it. And so we need to develop a way that can ensure data integrity and reliability. And so with that in mind, we have a few discussion questions that propose to the industry to come together to promote alignment. First one, what are the specific information exchange requirements needed to represent the activities and processes in the AEC industry? Think about the geometries we use, the human activities, environmental properties, energy models. Everything that surrounds us every day has to, at some point, be incorporated in our information. What super theories or base ontology exists that our industry can utilize? Now, again, instead of describing each one by ourselves, again, things exist. Math equations aren't going to change. Processes aren't going to really change. And so if they do, why don't we utilize things already utilized? Finally, what established domain ontologies exist? I mentioned a few. What others can be utilized and improved? What are the methods and benchmarks to validate and authenticate the currently available? So how can we, again, ensure integrity and reliability? And finally, what organizational bodies can be steward and oversee the development of these domain ontologies to promote consistency and alignment? So with these final questions, I'd like to thank you and ask for additional questions